Thank you, Joe. Next up, we have Thomas Sohmers, founder and CEO of Positron AI, our Diamond sponsors, to discuss the Gigawatt Gambit, the economic and environmental impact of global AI inference deployment. Welcome to the stage, Thomas.
Thank you. Hi. I'm Thomas Sohmers, founder and CEO of Positron AI. Just to give you a little bit of background, I got my start in the industry about a decade ago. I received this thing called Teal Fellowship that enabled me to actually drop out of high school and start a company. That was called Rex Computing. Developed a new process architecture for mobile base stations back before the recent semiconductor boom, back 2013 timeframe. Silicon wasn't exactly as hot as it now is with AI. But after that, got into the machine learning space through a friend's startup called Lambda, built out the Lambda GPU cloud in the 2019 timeframe, which has now become one of the largest pure-play GPU cloud service providers. And then had a 2-year stint at Grok, where I was director of technology strategy before starting Positron AI last year. But I think unlike a lot of these sort of talks, I don't want it to really just be a sales pitch for Positron. So I think one of the things I've been hearing the most over the summer are people concerned that we're in the middle of an AI bubble. And obviously I hope that isn't the case, and everything we're doing is assuming that AI is going to be as large as I think the vast majority of people here believe. But I think we need to have better, real fundamental understandings of why this isn't just a massive infrastructure spend wave that is going to take years or even decades to bear fruit, as what happened with the fiber rollout in the early 2000s. So first, are we in a bubble? My case for why we're not, really based on those base economics, try to get an understanding of why this is actually going to be something larger than any of us can imagine, and then a little sales pitch for Positron at the end. So yeah, Sequoia, one of the greatest venture capital firms of all time, had this blog post in June that really kickstarted this question. They were basically saying, based on all of the spend that just like the major hyperscalers are making on AI, there's a missing $600 billion in revenue to actually justify that. And this got a lot of traction, in circles, and Wall Street folks on the bear side really pointing at this, that hey, this is just .com all over again. And people love to point at a comparison of NVIDIA's stock price to Cisco's, and same example of fiber and of the railroad boom in the 1800s, et cetera. But I think they miss a couple of key fundamental points. Unlike the fiber rollout in the early 2000s, where they were anticipating a huge amount of demand to form and they were building out for that. I think a huge difference today is that NVIDIA is selling every GPU they make because people actually have applications that they want to run, and that demand is there today, and we're actually just trying to fill into it. But on top of that, kind of beyond the base economics, I think the real case is that for the first time in about the 250-year history of capitalism, we're actually entering a point where there isn't just a simple linear scaling factor to the core fundamental wealth drivers of capitalism, which we'll get into an economics lesson in a second. But my case is that actually there's a whole exponential growth curve to one of the core factors, which has just never happened before. And so fundamentally, this time it's different. I don't think I'm the only one thinking this, but the people that are making the multi-hundreds of billions of dollars spending decisions at the hyperscalers, et cetera, all fundamentally understand that and betting on it. So getting into the economics and history lesson, just under 250 years ago, in 1776, one of my absolute favorite books of all time. I read it when I was 15 and was mesmerized by the fact that a 250-year-old book, Adam Smith's The Wealth of Nations, could so eloquently describe a model that has actually held on for these centuries, and that it really just eloquently puts what are the core things that you need to be able to drive, the concept of wealth, but we all experience that as increases quality of life, new capabilities we can have, and has driven, 250 years of growth. So if we go back to 1776, the primary controllers and the established entities were the nation states themselves, and they were the ones driving that shift from mercantilism to capitalism. While today we've got some of the largest companies in the world, and I'll touch a bit on why I'm a little bit concerned about that. But in The Wealth of Nations, Adam Smith really came into the belief and labeled out that fundamentally all wealth was created through three things: land, labor, and capital. It was one thing in 1776, it's very different today, but the fundamentals are still there. So let's dive a little bit into each of those. So land, obviously the name kind of implies it's the thing that we actually build things on, but more than just the actual land and the facilities that get built on it, that also really represents all of the resources that we can collect. So all the silicon we have to create from the sand on beaches to steel and all of the power infrastructure that's needed, is fundamentally a consequence of extraction from the land, and there's externalities there that we also face. We'll talk about more of that in a second. From a capital perspective, over the past year especially, we've just seen absolutely massive investment rumors and announcements from the largest companies in the world. So the $100 billion Stargate supercomputer, Amazon is now actually just trying to buy land and buy out full nuclear power facilities to place data centers next to, and now multi-$100 billion investments that are now actually taking place at the state and even full nation level of trying to negotiate and buy to be able to build these things out. And I think some important comparisons to make is that the investment in AI-specific compute spend just so far in the past 2 years almost since ChatGPT already greatly expended the full nation effort of the inflation-adjusted spend of the Manhattan Project. If you look at the spend expected between now and the end of this decade, this is basically what these large companies have already committed to spending over the next 5-6 years, is towards about $1 trillion. So larger than the largest nation-state efforts that took place over decades. And I know I'm basically saying that Microsoft's last earnings call was saying that we don't have a direct line of sight for ROI, and that spooked some people on Wall Street. And basically, I'm saying you shouldn't worry about that, because fundamentally, land and capital, those two elements, I would say aren't fundamentally changed yet from data center perspective, and that we're actually putting more pressure on those things. So you need to use resources and build out things to a significant greater scale than any previous industrial revolution previously. But the thing that is different this time is that fundamentally what I'm arguing is that artificial intelligence unlocks this huge new capability game when it comes to labor. And so, one of just my favorite Adam Smith quotes, this is in the first chapter of The Wealth of Nations, was, labor was the first price, the original purchase money that was paid for all things. It was not gold or by silver, but by labor that all the wealth of the world was originally purchased. And, we're really entering this point where if you have, today, a DGX H100 box that can run Llama 405B, you have something that is actually better than a junior engineer in terms of programmer. Either think of that as something in the near future could replace or significantly augment a senior engineer, and be able to spin those up by the hundreds of thousands is something that we've just never experienced that sort of scaling jump in history. So I'll also now take this, let's try to discretely quantify some of these things. So, about 100-year-old formula is the Cobb-Douglas production function. So basically it's, the output or wealth times a productivity factor and then multiply that by the capital times labor. And basically, more or less, you're able to use this function and look at economies at a large scale and be able to say, hey, this is the output value. So a lot of economists, spend their whole careers just trying to figure out exactly how to play these numbers together and project things outwards. For simplification for the audience, I'll try to simplify that equation and use it through the rest of this sort of lesson. So, fundamentally, we'll say output or wealth is equal to a technology factor, which we'll just keep as a constant and say that that's a multiplier that changes over time. We have resources, so that's the land element of land, labor, and capital that encompasses everything I said before. The capital part isn't actually the money itself that is spent, but it's the all of the equipment, all of the machinery, all of the things that are actually bought with that. And then finally, labor. And so, the main point here is if we look at the first through third industrial revolutions, you fundamentally, if you look at the bottom equations there, just had linear factors. So when you were doing this sort of high-level math, you had a new industrial revolution, great new invention or technique that was able to add a multiplicative factor to either RC or L. The real argument I'm making is for this, what I'll just say is the fourth industrial revolution, specifically the emergence of artificial intelligence, is that I don't really care what the multiplier on R or C is. Like, you could kind of say that maybe even C from this multiplicative factor is effectively less because we now have to spend so much more money. We could potentially have, the fact that we're needing so much more resources, the actual effective resources that you can get goes down. But because L can now have an exponent factor, the fact that you can actually create new effective human labor is something that we've never seen in human history and kind of means that you shouldn't actually worry as much about that. For any computer scientists here, if you know big O notation, and if you think about the fact that, you really don't care about it, something being, ON squared, or et cetera, if you can actually have an algorithm that can just have linear growth. It's sort of the inverse of that. So what I would really be arguing is that what we're seeing today is really just the first order effects. We have massive power consumption demands, but the output of that is going to unlock this new labor element. And we can kind of see just the growth curve to today and then projecting out a few years in the future, that the AI-specific, the blue bar there, the AI-specific compute demand is growing at an absolutely absurd rate, and that by 2028 will be about 4.5% of the world's power. But I would say bigger, I think we can solve those problems. Yeah, it's going to cost a lot of money and take whole nations to sort of figure out the logistics of being able to spin up that much capacity and not have it impact other things. But I'm much more concerned about the consolidation problem. The only companies that are actually going to be using the vast majority of that energy are, in this case, really highlighting 5 of the largest hyperscalers. And I think the bigger problem there is just if what I'm saying is true, that this fundamentally is a new, hyper version of capitalism. If it's only five, what I think would then become the largest companies in the world that have access to that, that's I think an issue from a consolidation standpoint. But forget about the consolidation, just the company perspective. If we're going to be building out this much compute and scaling it out, and this is examples of gigawatts deployed just of AI compute this year versus 2030. The thing that market economics doesn't actually work out for is unpriced externalities. And so most people really know this as just what are the consequences on the environment due to industry. But fundamentally that by 2030, the AI-specific compute alone will be accounting for more than all of the households in the United States and Canada combined. 91 billion gallons of gasoline a year. It's pretty insane. And what's crazy is Microsoft's latest energy efficiency report, due to the new data centers that they're building in low cost of energy and high energy availability locations, actually has them getting worse efficiency on their water usage. So, the most efficient form of cooling that can practically be used is evaporative cooling, which requires a ton of water. And they're building these in data centers in Arizona and Nevada. So, the stress on especially regions that have very constricted water resources is immense. But all these companies know it, and I think the real thing that Wall Street hasn't quite figured out yet, or some parts of it, is the fact that this is all totally justified. This is the simplest bet you could make if you're Microsoft, where if you can have an 8X H100 box that costs ballpark $350,000, and you can deploy that, have operating costs in the $25,000, $30,000 range. It's low on the high end for a large company like that. But you could be generating, in this example, 30 tokens per second, like faster than human speed, reading speed, but it's doing that 24 hours a day, 7 days a week, doesn't complain about anything. That cost to that company, ballpark of $30,000 a year for even just say a relatively low-skilled employee. If we just say that today is the worst that this technology is ever going to be again, today this math works out. All right, so spent that. Hopefully, not too many glazed eyes for economics lessons, but talk a little bit about Positron. So we started in April of 2023. And fundamentally, we're trying to change that concentration fact, and also all of the elements talked about there, where fundamentally our focus is having the best performance per dollar, performance per watt, and scaling specifically for transformer models. We really saw after ChatGPT's launch this trajectory, and bet that you need to have specific hardware to be able to solve all of these problems. We've raised about $12 million to date, and now have a team of 21 people. But the thing I'm proudest to say is that in like 18 months from founding, we're actually shipping full production hardware as of last month. The actual technology we're leveraging to be able to do that are FPGAs. You can come to our booth. I'll advertise that in a minute. But fundamentally, we've been able to have a significantly reduced time to market and still be able to have, today, a 3 to 4x performance per dollar and performance per watt advantage over H100. And please come to our booth. You can actually see the real hardware there working and competing against NVIDIA. So I'll also, because I don't want this to be too much of a sales pitch, we'll shift from economics lesson to arithmetic intensity and how compute actually happens. A core factor in high-performance computing for decades is the fact that for any sort of high-performance compute, you're doing linear algebra, and that had the main focus for over the past decade has been just purely matrix multiplication. And that was the fundamental compute needed for things like convolutional neural networks. Now, the main element there is a matrix multiply without going too much into the weeds. Is fundamentally a compute-bound operation. You're doing multiple flops for every byte that you're doing. So it's an arithmetic intensity of greater than 1. It depends exactly on the algorithm, how large your matrix size is, a whole lot of details, but you can have 10 to 1, 100 to 1 flops to bytes. And so this is called a roofline diagram. And basically, bandwidth bound versus compute bound there. If you're to the left, if you're in bandwidth bound, it doesn't matter how many flops you've got. It doesn't matter, NVIDIA doubles, triples, quadruples the number of flops. If you're not increasing the memory bandwidth relatively the same, you're actually not going to be getting a speed up. So this is example for an H100. So on the right-hand side there, you can see, for a example convolutional neural network, which was, the mainstay of all, image-based machine learning for, last decade. Most focus was in the CNN domain. It's a very compute-bound application. So more flops you threw at it, the faster you got. But transformers are fundamentally, instead of matrix for the generation, the token decode portion of that workload, the inference, that is memory bound. So the arithmetic intensity is significantly less than 1. On average, in this chart is showing, a 1 to 10, so, 1 flop for every 10 memory references you're doing. But it actually gets much worse with that when you expand context window and increase model size. So, the thing that we should really be looking at, instead of, everyone talking about how many flops they have, is be looking at how much memory bandwidth do you actually have. And I would say even more importantly than that is memory bandwidth utilization. So, NVIDIA H100 has 3.35 terabytes per second of theoretical memory bandwidth. But as you can see here, the actual realized, the memory bandwidth utilization of that theoretical can drop, significantly below half of that in most scenarios. And so, this is, a specific example showing, instead of the previous diagram showing scaling of tensor parallelism, this is scaling the number of concurrent users, which, if we think that AI is going to, be used by everyone and to a large scale, you should be expecting that number in the bottom, the x-axis, to increase drastically. NVIDIA and in general, GPU, any compute-focused architectures are very heavily bound by this. And so their memory bandwidth utilization actually decreases, either as you try to increase tensor parallelism, increase the batch size, or increase context length, et cetera. While Positron, shown there at the top, fundamentally, we've built a memory architecture, which you can learn more about at our booth, that is able to achieve and sustain 95% of the theoretical memory bandwidth utilization. And so how that actually turns out, if we take the fact there that NVIDIA, even in a pretty good case, is about 30% of their theoretical memory bandwidth. So you pay for 3.35, you're getting closer to 1.1 terabytes per second in reality. The way that impacts is you would theoretically model and see the memory bound, just like the previous chart, it being right on that roof line. But because your effective memory bandwidth is so much lower, you're actually losing that 2/3 of your performance. So fundamentally, Positron, we're building systems that accelerate these class of applications because we have this much more efficient memory system design that both gives you, extreme memory capacity. So, our current product both leverages HBM and DDR directly together to also give massive amounts of capacity. And we're putting these things in full servers and selling those systems, both customers, for on-prem use cases and to cloud service providers that can use it for their customers. And fundamentally, like I said before, performance per dollar, performance per watt are the reasons you would go with us. But in this example of where you're constrained to say just to 10 kilowatts per rack, which is the vast majority of data centers that have been built around the world, you can only fit, for example, a single DGX. The technical TDP of that system is 10.2 kilowatts. Actually, fully running Llama 7DB, just under 6,000 watts. But you're stuck with just one of those. You could fit 5 of ours and still be comfortable, and thus be getting significantly greater overall aggregate performance and capabilities. We're actually shipping products. So this was now 3 weeks ago, delivering to first customer. We've got about half a dozen customers working with our hardware, mix of in their own premises and hosted. And yeah, I'd like to thank our seed investors taking a bet on us early on and moving us forward. So come check us out, booth 3536, and we're doing a product demo on the demo stage at 4:15 p.m. today. Thanks.